Hi everyone, welcome back to CS128 Honors, and today we're going to have our last lecture of the class, and it's lecture 15, and we're going to talk about shared state concurrency. So far we have covered multi-threading for about 1 to 2 weeks now, and we have learned a few things. We have learned how to create threads in Rust, let the thread do some work, and we have also learned how to use message passing using the NPSC type in Rust. So today we're going to learn something else, right? So we're going to learn multi-threading by sharing memory. So whenever we have multiple threads and we want them to be able to communicate with each other, there are two ways to do it. One is for them to pass messages to each other. The other way is for them to share some form of memory that they can all modify together, right? So today we'll learn how to do that in Rust and what are some of the problems with doing something like that. So when we first introduced multi-threading about 2 weeks ago, I made this toy example of a bank account and some of the problems that we have. So let's look at that again because today we'll try to solve that problem. So again, let's refresh the example. You have a bank account of $100 and friend A and friend B want to put $80 each into your bank account. So obviously at the end of the two transactions, you expect to have 100 plus 80, which is $260. So let's see what happens. So imagine if both friends went to the ATM at the same time, and the ATM asked the bank, think of it as like a server, right? And they ask, what is the balance in this guy's bank account right now, right? And the bank tells them both, okay, that the bank account is $100. Okay, so the ATM, at friend A calculates that the new balance is $180, right? Because the bank told him it's 100, we add 80 and you get $180. So friend A updates the bank server telling it, okay, the new balance is $180. Now, friend B also does the same thing. He got the value $100 from the bank and he added $80 to it. So he calculated that the new balance is $180 and he sends it to the server, right? So the bank also overrides the old $180 value with 180 again. And we realize the problem here, right? Which is you expected to have $260 at the end, but after both of the updates, you only have $180, right? And let's look exactly at why this happens. So how do we like update the transactions, right? So there's three main steps. One is we get the old value from the bank, we calculate the new value, and then we write back the new value to the server, right? So these are the three steps that are involved. And actually the key problem here is that these three steps must happen together without being interrupted, right? Which is not what happened with the bank. So for example, what happened just now was that friend A get the old value, which is $100, and friend B get the old value as well, which is $100, right? We don't want that to happen. We want friend A to get the old value, calculate the new value and update it, and then friend B will only get the updated new value instead of them both getting the same old value, right? So the idea here is that we want this series of operations to all happen together, right, without interruption. We don't want like one friend to get one value, the other friend get the same value, even though one friend is not done updating yet. So in concurrency, we call this an atomic operation. So basically, the series of operations must be atomic, and it means that the whole series of transactions will happen together without interference, or they just will not happen at all, right? So and the key idea here, like we said here, we only want one thread to modify the value at one time. So we want friend A to do the whole updating of $80 before friend B does the whole updating of $80, or vice versa. Friend B does all three steps before friend A does all three steps. So how will this look like, right? So this means that we need some kind of lock, right, on the value of the bank account to ensure that only one thread is updating it at one point in time, right? So we don't want it to, while friend A is trying to update it, friend B got the old value, which is what happened in our previous example. So let's introduce a lock to our example and see how it looks like now. So again, with the exact same scenario, we have $100 and both friends trying to get $80 each. And this time we introduce a lock, right? So this lock represents kind of a lock on the value of the bank account, right? Only for both the friends, they have to kind of acquire the lock. Think of it as like getting permission. They have to acquire the lock before they can start the transaction, right? And if they don't have the lock, they just have to wait till the lock is free and they can get it. So right now we have a lock and no one is owning the lock right now, right? No one holds it. So both of them ask the bank for the lock at the same time, right? And the bank would only give it to one person because only one person can hold the lock at once. So the bank decides to let friend A acquire the lock. So here we update that the lock is now held by friend A, and the bank tells friend A that the balance is $100, right? Meanwhile, at the same time, B also asked, but since the lock is given to friend A, B has to wait. So notice here that B does not get the old value of $100, like in the example we have before. B just cannot do anything, does not get any information from the bank, and just waits for the lock. So A updates the balance to $180, right? And then once we're done updating, we're done with the transaction. So we release the lock as well. So now nobody is holding the lock again. And the bank remembers that B is waiting for the lock, right? So the bank tells friend B, okay, now you own the lock, you're the only person with exclusive access. The balance is $180. So see, the difference here is that now we tell B that the balance is $180, right? Which is the correct updated value after friend A does the transaction. And then following this, B just updates a new value with $260, and then the lock gets released, right? Because nobody's using it. So the idea here that we want to show is that introducing a lock means that only one person can do the full transaction at one point in time, and it cannot be interrupted, right? And this helps to ensure that our code is correct in like how the transaction kind of happen. So how does this look like in Rust actually? So in Rust, the locks that we just talked about are called mutex. Mutex is short for mutual exclusion because we're excluding other people. When we get a lock, we're the only person, we're the only thread that's allowed to do an operation on the data, right? So mutex wraps sorry. So the mutex wraps some of the value inside, and in a way the mutex is a lock, as we remember, so it guards the data. So here we have two examples. For example, here I created a mutex, right, using mutex new, this is the syntax, and inside we protect this one number, so we initialize it to 5, right? So now we have this mutex and it protects this number, so only one thread can access it to update this number at once. So beyond that, the mutex can also be used to update, can also be used to protect slightly more complex data types, like a vector of numbers here, and I can use the mutex to kind of wrap this vector. So only one thread can modify this vector at once. So how does the locking actually work, right? So here again, I let num mutex be a new mutex that we initialize to 50, right, the value of 50. And how the locking happens is actually like this. So here we use braces to introduce a scope, and to kind of lock it, for a thread to lock the mutex, they will do mutex.lock. And then what this lock does is quite special, right? This lock attempts to acquire the lock. So acquire the lock means I try to get the permission to kind of modify the data within the lock. So if nobody is using it, the lock will get allocated to me, and this will return, right? Whereas if someone else is holding the lock right now, what this mutex.lock does is that it actually blocks the current thread. So the current thread just pauses here. The current thread is stopped here till the lock gets released. So let's say some other thread is holding the lock right now and they have exclusive permission. Once that other thread releases the lock, then we will get to use the lock, and that's when our thread will start running again. So in between that time, while someone else while someone else has the lock, the thread that calls .lock will have to block and wait, right? Now we look at what mutex.lock actually returns us, right? So lock returns this data type, which is a lock result that's wrapping a mutex guard, right? So it looks complicated, but it's actually quite simple. So lock result is essentially a result that we have known for quite long in Rust, right? So the result can be okay or error, right? So yeah, so we just assume that we don't get the errors here, and we just unwrap, and then the value inside is actually this thing called a mutex guard, right? So the mutex guard is a kind of smart pointer. It's okay if you don't know what a smart pointer is because we don't really teach it in this class, but essentially what we need to know is that the smart pointer, so remember here we introduced the scope, the smart pointer, so num is a smart pointer in this case because after we unwrap, So num is a smart pointer, and it means that when it goes out of scope here, like here, around here it goes out of scope, and beyond that num is not valid anymore. So when it goes out of scope, num is dropped. And what this really means is that the lock, so we've acquired the lock, right? Once it means that when we go out of scope and we drop it, is that we release the lock, right? And this is really, really important because imagine if some thread grabs the lock and then is done using it, done modifying the data that is kind of captured by the lock, but then never releases the lock. So all the other threads that actually need to access the data will wait forever, and they will never get to it because the thread that's holding the lock never releases it. So in a way, Rust helps us to solve this problem by automatically dropping the lock when it goes out of scope, right? Now, how do we actually modify the value underlying the lock that the lock wraps, right? So we use this star, which is called like a dereference. Some of you might have seen it by now. So essentially, when we do star num minus equals to 8, it just allows us to access the value that's kept within the mutex guard. So we've talked about mutexes, which is the lock that is used in Rust, and then we also have talked about the function, which is .lock, to actually call when we want to get exclusive access to the data inside it. So let's try to use it in multi-threading, which is the whole point of us having this mutex structure in the first place. So firstly, before I begin, I would like to say that this is a bad example. Like, this example will not compile, but it's important that we talk about it and why it doesn't compile. So here we define a new mutex, mutex new of a value 50. And then just like we learned in previous lectures, we spawn 10 threads, right? For I in 0 to 10. So we spawn 10 threads, and then within the thread, it takes in a function to run, right? So what it does is really simple. This is exactly what we showed in the mutex earlier. We just take the mutex, right? Mutex, and we lock it to try to get exclusive access, and then we try to increment the number by 1. So imagine if this 50 is like some bank account balance, we have 10 threads, and each of them is trying to increase the deposit $1 into our account, right? So that's all this trying to do. Really simple, really straightforward. So some of you who are looking at this will already start to see the problem with this, which is here we have the move, which means we want to move the ownership of this mutex value into the thread. Except this is invalid, right? Because this mutex is a normal object in Rust, and it has an owner, right? So once we move the ownership of mutex into the first thread, and we go back in the for loop to the second thread, the value mutex is already moved into the first thread. It's not there anymore. We can't use it. So how are we actually going to? The real problem here is how are we going to actually let 10 different threads have ownership of the same mutex? Because that's what we want, right? We want 10 different threads to kind of have ownership of the same lock, so that when they unlock, they will be working on the same data, right? So yeah, as I said earlier, the ownership of mutex cannot be moved into multiple threads. So so how Rust solves this is that it has two special types that actually allow a single object or single value to have multiple owners, right? So this is a bit different from what we have learned in Rust so far, which is every object has one owner, and then ownership gets transferred from one place to another, right? Here actually Rust introduces this type that lets this one object be owned by multiple different like places and functions or in a thread or whatever, right? So the first type is called RC, which is reference counting. And it's called reference counting because we are counting the number of owners here. And when the last owner goes out of scope, which means like nobody owns this value anymore, then this value is no longer kind of valid, and the value will be dropped, right? So it ensures that when someone is still, when there's at least still one owner that has ownership of the certain value, the value doesn't get dropped, right? So the other kind is ARC, which is atomic reference counting. So it does the exact same thing as RC, except that it's a version of RC that is safe to use for threads, right? Because when we have multi-threaded environments, there are some problems with concurrency, and ARC is a type that is safe to use in threads. So how are we going to use ARC to help solve our mutex problem that we have here? So again, we have this mutex that we defined earlier, right? Mutex new 50, and now the additional step is that we use ARC to wrap the mutex. So now this mutex is wrapped inside this arg.new, colon new, right? And when we have this arg mutex, multiple threads can have ownership of this same arg mutex object, right? And this arg mutex wraps the mutex inside, and so multiple threads can have ownership of this arg mutex, and underlying it, the data that is stored is the same mutex, right? So how we actually make that happen is in the for loop. Every time we create a new thread, we clone the arg mutex. So this is what we mean by creating multiple owners, right? So it's the same piece of data, it's the same piece of arg mutex, but we are cloning it, and it points to the same piece of data underneath it, right? So now each individual thread will get their own clone version of the arg mutex. Yeah. And notice that here in the thread, we do the exact same thing as if it was just a mutex, right? We just do clone.log.unwrap. We don't actually have to change the kind of functions that we call on it just because we're using the arg type instead of the mutex type. So so this example will compile and it will run normally, and this is what you basically have to do for the upcoming homework, right? And there is one last problem that we need to talk about in concurrency, which is deadlock. So deadlock means that two threads will wait for each other forever, basically, and then because of that, the program will never proceed, right? So how can this even happen? So imagine that for a particular thread to do something, it needs to acquire more than one lock. It needs to acquire like 2 locks or 3 locks or 4 locks before it can proceed, right? So an example that I always like to think of, again, we use our bank and bank accounts analogy. We want to transfer money from account A to account B, and to be able to do that in our concurrent environment, we need to we've learned that we need to lock the value of account A and lock the kind of value of account B, ensure that we're the only ones that can modify account A and account B before we do our transaction, right? So that's why we need to acquire the lock for A and acquire the lock for B, and only when we have both locks then we can start. So how about this? Let's take a look at an example. So we have a slightly different example this time, right? We have two friends, friend A and friend B. Friend A wants to transfer $500 from account X, imagine if there's an account X to an account Y, right? And friend B wants to transfer $1,000 from account Y to account X, right? So as we've stated before, now we need a lock for each account, right? So now we have a lock for account X and we have a lock for account Y. Now remember that for both friend A and friend B, they need to get the log of both account X and account Y before they're allowed to start. So let's look at how this happens. So friend A grabs his first log, which is account X, and then friend B tries to grab log Y, which is the first account, right? So they both ask the bank, one for log X, one for log Y, and the bank is like, okay, sure, nobody's using log X right now, right? So okay, friend A, you can have log X. So now log X is held by A, right? And same thing for friend B, the bank is like, okay, nobody is using log Y, so now log Y is assigned to B. Okay, it's all good so far, right? Now both of these two friends are going to grab the second log, because remember we said that we have to grab both logs before we can start the transaction. So now friend A wants log Y because he has X already, he wants Y, and same thing, friend B, they have Y already, so now they want X. So friend B asks for X, friend A asks for Y. Now remember we talked about locking, which means that it's exclusive, right? So when someone has it, the other person cannot have it until the person is done. So the bank would actually tell them, okay, your request is rejected, right? You have to wait because someone else has log Y. You have to wait till whoever releases log Y before you can grab the log. And friend B, same thing, the bank will say, okay, someone else has log X, so you can't do anything until someone else releases log X. So again, we have the rule that we need to acquire both logs before we can start the transaction. So now both friends are stuck, right? They both hold one log each, and they're both stuck because they can't proceed, right? And basically, they wait forever, and that is why it's called a deadlock, because friend A is waiting for log Y, which is held by B, and friend B is waiting for log X, which is held by A, and they're both waiting for each other, and they don't know that maybe, and they both cannot proceed, right? So if friend B has a chance of proceeding, then maybe it will release Y and friend A can use it, right? But that never happens, right? Because they're both waiting for a second log before they can move forward. So this is an example of deadlock, and it's still a common problem in a lot of systems today. And yeah, I mean the best way to kind of fix deadlocks is to prevent them. right? So to prevent deadlock situations from happening, the answer is actually really, really simple. What happens is that you just acquire locks in a certain order. So for example, in our example, friend A and B both need logs X and Y, right? So given that we have two logs, we kind of enforce an ordering. We always ask for the smaller letter first, for example. So we always ask for X before Y, right? Or if let's say friend A needs to acquire logs 1, 2, 3, 4, 5, and friend B also needs to acquire logs 1, 2, 3, 4, 5, right? So we have to make sure that in both threads you always ask for the logs in the order of 1, 2, 3, 4, 5, and this will prevent deadlock, right? And so this will actually show up for the homework. For the homework, we'll actually have a test case that tests for deadlock, and it's basically exactly same example as in this lecture, where we have a transfer from one account to another. So as long as you follow the rules where you acquire the logs in a certain order, like for example the smaller number first or the smaller letter first, you will not get into deadlock basically. So to recap, we talk about three main things today. We use mutex. The mutex is to lock the data so that only one thread can access it, right? And then we use arc to wrap the mutex so that multiple threads can have ownership of this same mutex. And then lastly, we talk about this problem called deadlock, and the way to solve deadlock is to acquire the logs in a certain order. Yeah, so announcements. This is the last lecture actually, and homework 12 is released. It's the last homework. So because the last homework we're giving you guys slightly longer, is due in 2 weeks on 9 November. And well, now we're starting to move into final project. So good luck with that, and remember to reach out for help if you do need it.